on IR spectroscopy, we'll focus on the aromatic substitution patterns and how we can use the bending region down here, among other things, to distinguish the substitution pattern on an aromatic ring. So first I'm looking at a monosubstituted benzene, just toluene, methylbenzene, and you'll notice we have two peaks down here, and they're about 700 and 730. Right? So at 696 we have a peak that has percent transmittance of 12, and at 729 a percent transmittance of 4. Those two peaks there are either indicative of a monosubstituted benzene, which we have in this case, or a meta-substituted benzene. It's difficult to tell the difference between the two, but a pair of peaks means that it is not a 1,4 para or a 1,3 meta-substituted benzene. sp2CH stretch here, right, between 3028 and 3087, those are the sp2 carbon hydrogen stretches, and then this typical region here, these 2873 to 2948, that's the sp3CH stretch. Sharp peaks at both 1500 and 1600 for the ring breathing. We expect to see that. And then we should see a methyl rock at about 1380. Probably that peak. The other distinctive pattern that you see for a monosubstituted benzene is in this region here, where not much else is, between about 1700 and 2000. We say this looks like a sawtooth pattern. Right? You can imagine that being a circular saw of some sort. That sawtooth pattern there is very distinctive for a monosubstituted benzene. An orthosubstituted benzene, in this case we've got 2-methyl-anisole, methoxybenzene, has the common name anisole. So it's either 2-methyl-anisole or 2-methoxy or orthomethoxytoluene, depending on whether you name it as a parent from the methoxy group or a parent with the CH3 group. sp2CH stretch, sp3CH stretch, right? So we have peaks both above 3000 and below 3000. So we've got both sp3 and sp2 hybridized carbons. We've got 1500 and 1600 peaks, right? Strong peak at 1497 with only 6, and a strong peak at 1603 with only 17% transmittance. Right? We expect to see that for a ring breathing. And then the single peak here at about 751, right? 7, that is distinctive for the ortho or 1-2 substitution pattern. Single peak somewhere around 750. You'll notice we also have peaks here. These are the carbon-oxygen stretches, single bond stretch for an sp3CH, right, at the lower energy, and an sp2CH at the higher energy. So you see that peak at 1246 and the peak at 1123. Those are our two different carbon-oxygen single bond stretches. Here we've got the same compound, but it's metamethoxytoluene or metamethylanisole or 3-methylanisole. And again, we've got two peaks down here, one at around 700 and the other one closer to 800. This is at about 775, right, in this case. So it is different from the monosubstituted benzene, where those two peaks were closer together at about 700 and 730, as opposed to about 700 and 780. But that's usually not good enough for determining that the substitution pattern is meta versus the substitution pattern being mono. You will notice the absence of the sawtooth pattern here, right? There's not that clear sawtooth pattern that we saw there for the monosubstituted benzene. So that helps to determine that this is a meta substitution. Right? We've got the same sp2 and sp3 hybridized carbon-oxygen stretches at about 1164 and 1261, right? Because it's an ether. 1500 and 1600, that's the ring breathing, and then the standard sp2 and sp3 carbon hydrogen stretching. A para-substituted benzene, a 1,4 substitution, our single peak here is at 818, as opposed to where it was for the ortho substitute, which was at about 750. So 750 there versus about 820 there. That single peak moves, whether it's 1,4 or 1,3. Standard, the rest of it, sp2 carbon hydrogen stretches, ring breathing at 1500 and 1600, and then the sp3 and sp2 carbon oxygen stretches in that 1000 to 1200, 1250 range that we would normally expect to see for an ether. So you see the ether peaks don't move around that much, but the pattern in this region in the 7 and 800 range changes. Right? Two peaks close together for monosubstituted, a single peak on the kind of higher energy side at around 750, lower energy side around 750 for orthosubstituted, two peaks further apart for meta-substituted, and then a higher energy around 820 or 850 for a single peak for the para-substitution. So sometimes you get better information. A para-substituted benzene is going to be much clearer in the NMR spectrum because you'll see those two doublets leaning towards each other, which you don't see in the ortho-substituted because there's no symmetry here. But the IR is a good confirmation tool for substitution patterns on a benzene ring.